Your database server crashes at 3 a.m. Without replication, your entire application is dead. Every user sees an error page. Replication is how Netflix, GitHub, and Slack stay online when servers fail. Let me show you how it works. Database replication. High-level design, day 8. The most common replication pattern is master-slave, also called leader-follower. One database server is the master or leader. It handles all write operations. Inserts, updates, deletes, all go to the master. Then the master copies or replicates every change to one or more slave servers, also called followers or read replicas. The slaves serve read queries. Since most applications are read-heavy, maybe 90% reads and 10% writes, you can scale read throughput by adding more slaves. 3 slaves means roughly 3 times the read capacity. If the master crashes, you promote one of the slaves to become the new master. This is called failover. The promoted slave starts accepting writes, and the other slaves point to the new master. This gives you high availability. Your application stays online, even when a server dies. There are 2 ways to replicate data: synchronous and asynchronous. With synchronous replication, here is the flow. The client writes to the master. The master sends the change to all replicas. The master waits for all replicas to confirm they received and stored the data. Only then does the master acknowledge the write to the client. The advantage is 0 data loss on failover. Every replica has every write. You get strong consistency and read after write guarantees. The disadvantage is higher write latency. Every write waits for the slowest replica. If one replica is slow or down, all writes are blocked. With asynchronous replication, the master acknowledges the write immediately after storing it locally. Replicas catch up in the background. The advantage is low write latency. Writes are fast because they do not wait for replicas. A slow replica does not block anything. The disadvantage is replication lag. Replicas may be seconds behind the master. If the master crashes before replicating a write, that data is lost. Reads from replicas may return stale data. Most production systems use semi-synchronous. One replica is synchronous for safety. The rest are asynchronous for performance. This gives you one guaranteed up-to-date replica for failover, without the latency penalty of full synchronous replication. Multi-master replication, also called multi-leader, allows multiple servers to accept writes. This is critical for multi-region deployments. Imagine users in the US, Europe, and Asia. With master-slave, all writes go to one master. If the master is in the US, European and Asian users have high write latency. With multi-master, each region has its own master. US users write to the US master. European users write to the EU master. Each master replicates to the others. Low write latency globally. But here is the catch: write conflicts. If 2 users edit the same row at the same time on different masters, you have a conflict. Both writes are valid locally, but they contradict each other. You need conflict resolution. Last write wins is the simplest. The write with the latest timestamp wins. But clocks can be skewed. Merge strategies try to combine both changes. CRDTs, conflict-free replicated data types, are data structures designed to merge automatically without conflicts. Multi-master is significantly more complex than master-slave. Use it only when you truly need multi-region writes. Quorum-based replication is used by distributed databases like Cassandra, DynamoDB, and Riak. Instead of a single master, data is written to multiple nodes simultaneously. The key formula is R plus W greater than N. N is the total number of replicas. W is the write quorum, the number of replicas that must acknowledge a write before it is confirmed. R is the read quorum, the number of replicas you must read from. If R plus W is greater than N, at least one of the nodes you read from will have the latest data. For example, with N equals 3, if W equals 2 and R equals 2, R plus W equals 4, which is greater than 3. Strong consistency. At least one node overlaps between the write set and the read set. If W equals 1 and R equals 3, writes are fast but reads are slow. Every read checks all 3 nodes. If W equals 3 and R equals 1, writes are slow but reads are fast. One node is always enough. If W equals 1 and R equals 1, Fast as possible, but only eventually consistent. The power of quorum is tunability. You can adjust consistency per query. Critical operations use strong quorum. Analytics queries use eventual consistency for speed. Replication introduces different consistency models. Strong consistency means every read returns the latest write. This requires synchronous replication or reading from the master. Higher latency, but no surprises. Read after write consistency is weaker. A user always sees their own writes. If they update their profile, they see the update immediately. But other users may see stale data briefly. You achieve this by routing a user's reads to the master for data they recently wrote. Eventual consistency means replicas converge over time. After a write, there is a window where different replicas return different values. Eventually, they all agree. This is the default for asynchronous replication and is the lowest latency option. Replication lag causes real problems. A user updates their profile picture, hits refresh, and sees the old picture. That is because the read went to a replica that has not caught up yet. The fix is read after write consistency for user-owned data. Route their reads to the master or to a replica that is confirmed up to date. Here is your interview framework for replication. Start with the workload. Read heavy? Master-slave with read replicas is the standard answer. It is simple, well understood, and scales reads linearly. Need multi-region writes? Multi-master with conflict resolution, but always mention the complexity cost. Need tunable consistency? Quorum-based like Cassandra or DynamoDB. You can adjust per query. Need zero downtime failover? Semi-synchronous replication with automatic promotion. Real-world examples. MySQL uses master-slave with async replication by default. Semi-synced available for critical writes. PostgreSQL uses streaming replication with per-transaction sync commit settings. Cassandra uses quorum-based replication where you set W, R, and N per query. DynamoDB uses a leader for writes with quorum reads, eventually consistent by default, but strongly consistent reads available per request. The pro tip is to always mention the cap theorem. Replication gives you partition tolerance. Then you choose between availability and consistency. Most production systems choose availability with eventual consistency and handle the edge cases with techniques like read after write for user-owned data. 5 things to remember. Master-slave replication has one writer and multiple readers. It scales reads linearly, and you promote a slave on master failure. Multi-master allows multiple writers for multi-region deployments, but requires conflict resolution using last write wins, merge strategies, or CRDTs. Synchronous replication means zero data loss, but higher latency. Asynchronous means low latency, but possible data loss. Semi-synchronous gives you the best of both worlds. The quorum formula R plus W greater than N guarantees you read at least one node with the latest data. Tune W and R based on your latency and consistency requirements, and in interviews, always mention the cap theorem and pick your replication strategy based on the read-write ratio and consistency needs of the system.